Imagine waking up one morning and reaching for your smartphone, only to find that it does not work. You glance at the television, but the screen stays dark. You try to start your electric car, and it refuses to move. Even the internet, satellites, and global navigation systems seem to vanish from existence. This scenario may sound like science fiction, but it reveals a deeper reality. Just how dependent we are on something we rarely see or hear about, rare earth elements. These tiny elements, hidden deep within rocks, have become the silent heart of modern technology. Without them, the technological progress we take for granted would grind to a halt, and everyday life would change in ways that are difficult to imagine. In this story, we follow rare earth elements from deep underground to factory floors, from scientific laboratories to political offices and economic boardrooms, to understand how simple chemical elements became strategic assets in an increasingly complex world. In the late 18th century, a group of scientists in Northern Europe, particularly in Sweden, were studying dark-colored rocks that appeared ordinary to the naked eye. As they analyzed them, they discovered substances unknown at the time. Analytical tools were far less advanced than today, and the discovery of even a single new element was considered a major scientific achievement. What no one expected was that these rocks contained an entire family of previously unknown elements. Over the years, chemists gradually separated and identified these elements one by one, giving rise to what we now call rare earth elements. Although scientists recognized their scientific value early on, their economic and technological importance did not become clear until centuries later, when the technological revolution of the 20th century accelerated and demanded materials with extraordinary magnetic, optical, and electronic properties. At first glance, the term may suggest that these elements are nearly extinct or found only in a few places on Earth. The reality is more nuanced. Many rare earth elements exist in the Earth's crust in quantities comparable to, or even greater than, well-known metals such as copper or lead. The challenge lies not in their presence, but in the way they occur. Rare earth elements rarely form concentrated, easily extractable veins like gold or silver. Instead, they are dispersed in low concentrations and mixed with other elements, making extraction and separation technically complex and expensive. Thus, they earn the label rare not because they are absent, but because isolating and processing them into usable industrial materials is exceptionally difficult. Over time, the name persisted, even after scientists realized that the real question was not, do they exist, but rather, can we extract and process them efficiently and safely? Consider a tiny piece of neodymium, no larger than a bean. It may form part of a powerful magnet used in a small earbud, an electric vehicle motor, or a hard drive inside a laptop. On its own, the piece appears insignificant, yet its importance becomes immense when we realize that millions of devices worldwide depend on such components. Inside an electric vehicle factory, components move swiftly along precise assembly lines. At the core of the electric motor, magnets made from carefully engineered blends of neodymium and other rare earth elements are installed. These magnets provide high power and energy efficiency while remaining lighter and more compact than alternatives. They are not optional extras. They are essential for enabling electric vehicles to travel longer distances on a single charge. Elsewhere, in factories producing televisions and tablets, elements such as europium and terbium are used to create vivid, pure colors. The deep reds and bright greens displayed on modern screens are the result of complex chemical processes powered by these elements. In the renewable energy sector, wind turbines spinning above hills and coastlines rely on high-efficiency permanent magnets made from the same family of elements. Thus, the journey of rare earth elements stretches from underground mines to towering wind turbines, from chemistry labs to the pockets of billions of people through smartphones and smart devices. Beyond civilian applications, rare earth elements play a critical role in defense and military technologies. In dark rooms equipped with night vision systems, soldiers rely on devices containing these elements to convert faint light into clear images. Radar systems, precision-guided missiles, and satellites orbiting Earth all carry the unmistakable imprint of rare earth technology. For this reason, these elements are often classified as strategic resources. Any disruption in their supply chains does not merely raise the cost of electronics, it can affect the military balance of power between nations. Behind the technological brilliance enabled by rare earth elements lies a less glamorous and far more troubling environmental story. To reach the purity required for high-tech applications, these elements undergo extensive crushing, grinding, and chemical processing. In mining regions, massive amounts of soil and rock are removed, and powerful chemicals are used to separate elements from one another. In some cases, these processes leave behind toxic waste ponds, contaminate groundwater, and damage soil beyond easy recovery. Communities near mining sites may suffer serious health consequences as a result of pollution. This creates a painful paradox. Materials that enable clean energy technologies such as electric vehicles and wind turbines may themselves be extracted in environmentally harmful ways elsewhere in the world. This tension between technological advancement and environmental protection has turned rare earth elements into a focal point of global debates about sustainability and the limits of acceptable environmental sacrifice. A glance at the global production map reveals one overwhelmingly dominant player: China. Over several decades, China invested heavily in mining and processing capabilities, becoming the world's primary supplier of rare earth elements. Its dominance lies not only in extraction but also in its advanced capacity to refine, separate, and transform these materials into industrial-ready products. As time passed, other nations recognized the risks of relying on a single source. These elements cannot be easily substituted, and any political or economic decision affecting exports can instantly impact automotive factories and major technology companies worldwide. Thus, rare earth elements have become a powerful geopolitical lever. In response, countries such as the United States, Australia, Canada, Japan, and members of the European Union have begun seeking alternatives, opening new mines, developing domestic processing capabilities, and investing in recycling and research into potential substitutes. In laboratories around the world, researchers are grappling with persistent questions. Can we create powerful magnets without neodymium? Can display technologies function without europium and terbium? Are there new materials capable of replacing rare earth elements in certain applications? So far, no universal substitutes have emerged. However, advances have reduced the quantities required or improved device efficiency. At the same time, another crucial approach has gained attention: recycling rare earth elements from old devices. Smartphones discarded after a few years still contain valuable rare earth elements. The same is true for old hard drives, broken screens, and small electric motors. Collecting, dismantling, and extracting these materials is complex and costly, but it grows increasingly important as global demand rises and environmental awareness deepens. Although recycling efforts remain limited compared to overall demand, they represent a critical piece of the broader strategy to manage these strategic resources more responsibly. Looking ahead, demand for rare earth elements is expected to rise sharply. Electric vehicles are becoming more widespread, renewable energy projects are expanding, and smart devices have become integral to the lives of billions. All of these trends rely to varying degrees on rare earth materials. At the same time, production cannot expand indefinitely without accounting for environmental, social, and economic costs. This reality is forcing governments and companies to rethink design and manufacturing approaches, asking how devices can last longer, how they can be dismantled more easily, and how technological progress can avoid becoming a burden on the planet and its people. There is also a critical political dimension. Competition among major powers to secure supply chains may lead to tensions, economic shocks, and shifts in global alliances, reshaping investment priorities and international relations. At the end of this journey, we return to a simple truth. Tiny elements we never see are embedded in nearly every device we use. Rare earth elements exemplify how science, technology, economics, and politics can converge around a handful of atoms. From mines to smartphone screens, from car motors to wind turbines, from operating rooms to outer space, these elements quietly write their story, leaving a profound imprint on the world we inhabit. Understanding this story helps us not only appreciate modern technology, but also reflect on our responsibility toward the environment, the resources we consume, and the choices that shape our future. We may never see these elements with our own eyes, yet their impact is present every time we light up a screen, charge a battery, or rely on a system whose inner workings we rarely question. They are indeed small treasures, whose influence on our world is immense.